Now our third online speaker is Jaime Santos. He is now in Durham University, but he's also from Universidad Autónoma de Madrid, and he's going to talk about on the fundamental groups of RCD spaces. Thank you, Jaime.
Okay, thank you very much. First of all, to the organizers for inviting me to give this talk. This is based in joint work with Sergio Zamora Barrera, who is a postdoc in Max Planck Institute in Bonn. And well, I will talk about, as Juan Carlos said, about fundamental groups and RCD spaces. I will define what RCD spaces are and give some motivation, just like Chiara did. And I will also try to give some motivation about the fundamental groups and things you can find when you're working in non-smooth settings. But let me begin. So in the last 10 years, the study of synthetic notions of Ricci curvature has seen a fast and deep development. Here by synthetic, we refer to a notion that does not rely on any smoothness assumption of the underlying space. And the plan for our talk is the following. First, I will talk about convergence of spaces. That is, I will talk about how one can define a notion of sequences for which the elements are metric spaces or Riemannian manifolds, and what we can study about these sequences. Then I will talk about synthetic Ricci curvature and mention some of its properties and examples. And finally, I will talk about the structure of fundamental groups, in which I will delve a bit into things that are a bit unusual, like, for example, spaces where you don't have a universal cover, or where the universal cover is not so nice, for example. So let's begin with how spaces converge. Okay, consider that you have two compact spaces, x and y, and some function f. It is an isometry if it satisfies two things. The first one is that for every 2 points, x1 and x2 in x, the distance between f of x1 and f of x2 equals the distance between x1 and x2. That is, it preserves the distance. The second is that for all y in y, there exists some x such that f of x equals y. That is, it is surjective. Now, suppose that you have given an epsilon greater or equal than 0. Then an epsilon isometry will be a function, again, from x to y, such that it is almost distance preserving. That is, that for every 2 points, x1 and x2, the distance between f of x of 1 and f of x of 2 differs with the distance of x1 and x2 by epsilon. And the second condition is that it is almost a surjection. That is, for every point y in y, there is some point f of x, which is a distance epsilon. A couple of observations that we need to make is that, in general, epsilon isometries do not need to be continuous. These are just maps that satisfy these two things. And the second is that given an epsilon isometry, one can always find an almost inverse of it. That is, we can always find an f tilde now going from y to x, such that it is a 4 epsilon isometry. So you lose something, but is not so important. So now that we have epsilon isometries, what can we do with them? Well, you can say the following. Consider a sequence of compact metric spaces, xn dn, and we will say that they converge to another compact metric space xd if there exist epsilon n isometries, f of n, such that the epsilon n converges to 0. So we have a notion of convergence for compact metric spaces. So with this, the natural question one asks is, if I have a sequence that converges to some space XD. What can we say about the topology or the geometry of X in terms of the Xn or vice versa? We have something. And well, the answer is that, well, not much really. Some things can happen. And let's see some examples. The first one, consider a sequence of spaces Xn, which are just tori, such that one of the components is getting thinner and thinner. Just look at the picture. You take the squares identified and you make one of the sides shorter and shorter. And intuitively, you converge to S1. So just to give examples of epsilon isometries, you can take the inclusion from the S1 to each of these xn's, and notice that it is an 1/2n isometry. And by the thing I mentioned before, you can take the map that is the almost inverse. And so, by definition, the xn converges to S1. So here we can observe that both the topology and the Hausdorff dimension may decrease in the limit. But some other things can happen. A second example, you take two spheres, you join them with a cylinder, and you make that cylinder thinner and thinner. So in the limit, you have the two spheres joined by a segment. And so the limit is clearly not a manifold. So even though all of the elements can be taken to be very smooth and very nice, the limit might not be so nice. Another thing that could happen, say you have this sequence, you have a ring with some thickness, and at each state, you make it thinner, and then you glue another ring at a point, just like in the picture, and you repeat this process. You make it thinner, and then you glue another thing, another circle. So in the end, you end up with the Hawaiian earring. And the thing is that this limit has very pathological properties. For example, here I put that the isometry group is not a Lie group, but in terms of universal covers, there can also be strange things happening with this space, which will appear later again. But okay, I've given examples of things of bad things that can happen, but not all is lost. We can, impose some reasonable geometric restrictions on the elements of the sequence, and maybe we can say something about limits. For example, take some numbers k in R, n greater than 1, and d a positive number. Let M, K, and D denote the set of Riemannian manifolds, Mg, such that the dimension of M is bounded from above by N, and the Ricci curvature is bounded from below by K, and the diameter is bounded above by D. Then Gromov proved that this set is pre-compact with respect to the convergence that we just defined. The interesting thing is that given that limits of Riemannian manifolds are in general no longer manifolds, this motivates the search for a notion of lower Ricci curvature bound in a possibly non-smooth setting, because at least we would like to study what the structure of these limits are. So before I continue, I would like to make a couple observations. First one, just as Chiara mentioned in the talk before, in order to properly characterize lower Ricci curvature bounds, one needs to involve more information. So we require the volume, for example. And so instead of only dealing with metric spaces, we'll need to equip them with our reference measure. The typical example is you have a Riemannian manifold with the distance induced by a Riemannian metric and the volume with some density. But some other things can appear. The notion of convergence I presented is called Gromov-Hausdorff convergence. And this can be extended to non-compact spaces. However, there we need to fix distinguished point. And then we need to talk about pointed convergence. So we need to keep track of the space X, the distance, but also of this distinguished point. So now that we have a bit of motivation about the convergence of spaces, let me talk a bit about the curvature bounds in this non-smooth setting. These are the spaces we'll be working with. Let XDM be a complete separable metric space equipped with a radon measure M. As I said, the example to keep in mind is a Riemannian manifold with the distance induced by the metric G. And for the measure, take the volume with some density. Now we will need an auxiliary space, which is a space of probability measures with finite second moments. That is probability measures such that the integral of the square of the distance from a fixed point x0 is finite. And what can we do with this space of relative measures? Well, we can define the distance, which is called the L2 Wasserstein distance, given two measures, M1 and M2. One can define the Wasserstein distance between them in the following way. In the right-hand side of the equality, you consider the integral of the square of the distance with respect to a measure pi, where pi is a measure now in the product of x with itself, such that it has marginals M1 and M2. So minimizing this integral with respect to pi is known as the Kantorovich optimal transport problem. And this can always be solved. And so actually this infimum is minimum. And we can use this to define a distance on the space of probability measures. An important feature of this space is that it is complete and separable, and that furthermore, it is geodesic if my original space is geodesic. Now, a couple more things that I will need. Given a measure mu in P2 of x, such that it's of the form rho times the reference measure, that is the radon-Nikodym derivative with respect to m is rho, we can define the following entropy functions. Un of mu will be the integral of rho to the 1 minus 1 over n multiplied by minus n. And we also have the u infinity of mu, which is the integral of rho log rho. Why do we need them? Well, because again, as Chiara mentioned before, if we are dealing with Riemannian manifolds, then having the Ricci curvature bounded from below by k is equivalent to the functional, I put it here, u infinity, being k convex. So it is convex in a suitable way. And the thing to notice here is that the condition on the convexity of u infinity does not rely on any smoothness of the space. We can define the Wasserstein space. We can talk about these entropy functionals without really caring if the reference measure is volume or whatever other thing that we can put. So this definition makes sense to generalize what we want. And this is exactly what it's done. Lotz, Sturm, and Villani defined that a metric measure space satisfies the CDKN condition if the entropy functional UN is K-convex along geodesics in the Wasserstein space. Just to at least give you something, in the case where K equals 0, the K convexity looks like this. You have on the left-hand side the integral of ρ t, which is the density of the geodesic between mu0 and mu1 at time t. And on the left-hand side, you have the convex combination of the functional evaluated at mu0 and mu1. Okay, so we have a notion of a non-smooth Ricci curvature. And it has some nice properties. The first one is that it is compatible with the smooth setting. That is an n-dimensional Riemannian manifold, M is CDKN if only if its Ricci curvature is bounded from below by K. The second one, and that's really important, is that it is a stable condition under Gromov-Hausdorff convergence. That is, if I take a sequence of CDKN spaces and I know that they converge, then the limit is also CDKN. The Hausdorff dimension of X is bounded from above by N. So you think of the CDKN condition as having Ricci bounded from below by K and the Hausdorff dimension bounded from above by capital N. And we can also actually say some things about the reference measure. That is that we know that it is doubling. This means that I can bound from above the measure of a ball of radius 2r in terms of the measure of a ball of radius r times some constant. So even though the choice of the distance and the measure may seem arbitrary, they are actually connected, at least in some way. And more importantly, the metric measure space is proper. So in particular, it is locally compact. And well, we can do geometric constructions with these spaces. For example, we can take products of them, we can take cones over them, and we can take suspensions. And these were all constructed by Ketterer in 2015. So one thing to consider is that if our goal is to work with spaces that reflect Riemannian behavior, we find that the class of CDKN spaces might be a bit too broad. Yeah, we generalize the case of Riemannian manifolds, but there might be more spaces than what we want. And that is the case of compact field manifolds, for example. They satisfy the CDKN condition for some K and N, and it was proved by Otta in 2009. But on the other hand, we also have that if a smooth Finsler manifold is obtained as a limit of Riemannian manifolds with Ricci curvature bounded from below by K, then this Finsler manifold must actually be Riemannian. So it justifies that these sort of spaces do not live where we want. And this was done by Chigger and Kolding. So we need to get rid of them in some way. And for that, we need to impose further restrictions on the spaces that we will be using. And for that, one looks at Sobolev spaces. By work of Chigger, Haiwash, and Shanmungalikam, amongst others, one can develop a Sobolev calculus for general metric measure spaces. In particular, one can talk about Sobolev functions and the modulus of the gradient of a Sobolev function. I won't give the definition, but I will say that an infinitesimally Hilbertian space is a metric measure space such that the sublab space W12 is actually a Hilbert space. In general, it will only be a Banach space. The crucial observation here is that a Finsler manifold is infinitesimally Hilbertian if and only if it is actually Riemannian. So with this, the natural definition given by Ambrosio, Gigli, Mondino, and Savary, first in the compact case and then for the non-compact, is that a metric measure space will be said to satisfy the Riemannian curvature dimension condition, RCD, if it is both CDKN and infinitesimally Hilbertian. So, under this more restrictive condition, we do still have some good properties. For example, we still have compatibility with the smooth setting. So Riemannian manifolds are still RCD conditions. And we also have stability with respect to convergence of metric measure spaces. That is, limits are still RCD space. But we also get more geometric results. We have a splitting theorem, just like in the smooth case by Chigar and Gromov, which says that if you have an RCD0n space, which contains a line, that is, there's an isometric embedding of the whole R into our space X, then it is actually isomorphic to a product of Y times R with a product metric and a product measure. And the thing here is that this space Y is an RCD0 n-1 space. But we also have a couple more things I would like to mention. Is that first, the isometry group of an RCD space is a Lie group, just only in the Riemannian case. It was joint work with my thesis advisor, Luis Guijarro, and which was independently obtained by Gerardo Sosa. And now that it is known that the isometry group is Lie, one can also get new examples. For example, if you have a G, a compact Lie group acting by measure preserving isometries, that is, the group G not only preserves the distance, but also fixes the reference measure, then the quotient space X mod G with a quotient metric and the quotient measure is still RCD. And this was done by Galaz Garcia, Kell, Mondino, and Sosa. So we do get new examples using these isometry group actions. Okay. So now that I've given the setting, I can move on to the last part of the talk, which goes about universal covers and their fundamental groups. And the thing here is that, okay, we're dealing with spaces which are only metric measure. So they are no longer smooth. So we need to be careful. Why? Because, well, strange things can happen. And let me give you a couple of examples. On the left-hand side, we have the Hawaiian earring that appeared in the beginning of the talk. And this space actually does not have a universal cover. It's something very different from the smooth case. And the idea for this is the following. If you're in a length metric space, consider you have a positive delta, and you cover your space with balls of radius delta. And the thing is that for this cover, you can find a covering space that is given in terms of this delta. Let's call it X delta. So you have one cover. Next, you take some smaller delta, say delta over 2. And you cover again by smaller balls, you get a new covering space. And the thing is that the covering space x delta over 2 will also cover x delta, the first covering. So you have an order of covers, and it was proven by Mondino and Wei that if that length compact metric measure space has a universal cover, if and only if these delta covers stabilize. That is, you can find a small delta such that these will be the associated covering X delta will actually be the universal cover. Okay, what happens with the Hawaiian earring? Notice that if you look for balls around the point where you are gluing all of these circles, no matter how small you take it, you will find something that just looks like the Hawaiian earring. So there's no way that it's a bit more complicated than that, but there's no way that you can expect the covering to stabilize. You can still give new and new coverings because you will still have like so much left. You're basically in the same situation as when you began.
Nice.
So the space doesn't have a cover, a universal cover. Now for the space on the right-hand side, which is called the Griffiths twin cone, you construct it as follows. You take the Hawaiian earring, you take the cone over it, you take another copy of this cone, and you glue them by this annoying point where that gave us problems before. So that it looks like in the picture. And the thing is that this space does have a universal cover. It is itself, but it will not be simply connected. Why? Because if you take loops based around this problematic point, and you turn on the right, and then you give a turn on the right, then you give a turn on the left, and you keep repeating an infinite number of times. So you have a loop, and now you want to contract. What you would need to do, you would need to take, say, the one on the right, all the way up to the tip of the cone, and then contract. Then you have the part on the left, for which you have to take it all the way down to the other tip of the cone, and then contract. And you have to do this an infinite number of times. So if you think about something like the function sine of 1 over x, and you notice that you have this oscillation between the upper tip of the cone and the lower tip, and there's no way that you can expect that to be continuous. So the Griffiths twin cone cannot be simply connected. So strange things can happen for metric spaces, but fortunately for an RCD space, Mondino and Wei actually proved that RCD spaces do indeed have universal covers, and even more, these universal covers are again RCD spaces. The basic idea again is just proving that these delta covers given by coverings of balls actually stabilize. And well, then once they find the universal cover, they can lift the RCD condition from the space X to X tilde locally. So for each point, you have this good neighborhood, which can be lifted isometrically, and then they just lift the curvature condition there. And it is known that the RCD condition, if you have it locally, then you can extend it globally. So you end up with an RCD space. The only problem, however, is that at the time they were unable to prove whether the universal cover is simply connected, but they do obtain some results. For example, they obtain that if you have an RCD K space with K positive, then the group of the transformations is finite. They cannot talk about the fundamental group since it is not, it wasn't known that it is simply connected. But very recently, Wang proved that indeed the universal cover of an RCD-K space is simply connected. And I won't go over describing the proof, but it took some work to actually find a good argument that could be used for a simply connected case. I will just mention that it was first, it used some ideas for first looking at limits of Riemannian manifolds and seeing how this condition behaves about the universal cover being simply connected, but it requires a bit more work to actually get it if you only have an RCD-K space. And well, now I just mentioned a couple of results. Together with Sergio, we were able to extend some results previously obtained by Kapovic and Bilkin in the smooth setting. I will just mention a couple. The first one, if you have an RCD space XDM with diameter bounded from above by D, by a positive number D, then the fundamental group can be generated by at most C elements, where the C depends on K, N, and D. It is written in this way just to mimic the bound in the smooth case, just in case you're wondering. And the second result I would like to talk about is that if you have an RCD space with the diameter bounded from above by D, and if you know that the universal cover X tilde is compact, then the diameter of X tilde will be bounded from above by, again, a universal constant that only depends on the N, the K, and the E of the original space. And again, I just put sort of like mimicking the bound in the smooth setting. And I will actually talk about a bit about in the last couple of minutes about the proof of this result. And let me give a sketch of the proof. We will proceed by contradiction. That is, we assume that there is a sequence xi converging to x infinity, such that all the diameters of the xi are bounded uniformly by D, but such that the universal covers xi tilde converge to an unbounded x tilde infinity. Here I actually didn't write it properly, but because you do need to have the convergence in the pointed sense, and then probably take a subsequence that again converges, but let me just write down like this. And let us notice a couple of things. First, that the limit x tilde x infinity is compact, as we have the uniform bound. The converging universal covers, for them we have that the fundamental groups of phi1 xi act isometrically on each of them, and by a result of Fukai and Yamaguchi, there exists a closed subgroup, and so a Lie group is the limit x tilde infinity must also be an RCD space, gamma, such that the convergence is actually in the equivariant Gromov-Hausdorff sense. Okay, I didn't define this, but let me just explain it like this. We had these epsilon isometries between the spaces, which were like the almost isometries. And for the groups, pi1, xi, and gamma will have maps that can be thought of as almost group homomorphisms. And these epsilon isometries and these almost group homomorphisms are related in a way compatible with the isometric action on the x tilde I. Again, giving that the epsilon isometries are actually almost equivariant, so that everything fits correctly. But just the brief idea, keep in mind that you have the epsilon isometries for the spaces xi, and you have these almost homomorphisms for the pi1, xi, and the gamma. So you have some approximations for the groups. So we also have by Fukayo-Yamaguchi that if we take the quotients of xi tilde I with respect to the fundamental groups, we have Gromov-Hausdorff convergence to x tilde infinity modulo gamma. But we recall that since we're dealing with universal covers, each of the elements of the sequence is actually the xi. So we must have, since this sequence already converges, that the x infinity equals x tilde infinity quotient by gamma. And now, since the x infinity is compact, this forces the group gamma to be non-compact. That is because we're assuming by contradiction that the x tilde infinity is non-compact.
Pero allá pues.
And now the thing is that here we need to use some extra tools. We use tools from Broliard, Green, and Tao, which in their paper from 2012, they studied how can one approximate Lie groups via discrete groups. They prove some results about the maps that we use in the approximation, and we use them in conjunction with the fact that we're dealing with universal covers to find discrete approximations Fi from the fundamental groups to gamma, which are in what we call clean. The idea is, I won't go into detail, but for each group, you have what is called a determining set. That is, it will be a generating set such that the group can be presented in terms of elements of that set and a relation of words given by words of length 3. So you have this presentation of a group. This is true for any group. And what we ask for these approximations is that one can find a determining set for gamma and determining sets for the xi, such that these approximations are controlled in the sense that, say, the determining set for gamma is called S0. Then the inverse image of S0 is contained in all of the determining sets for each of the pi1 xi for sufficiently large I, and that this Si can be controlled by the inverse image of an appropriate compact set. Okay, a quick example. if you are in, or well, what we actually prove is that the determining sets that work are given by elements of the fundamental group, such that they displace the base point where we're taking the fundamental group a fixed amount. The displacement is less than 40 times the diameter or something. We have a uniform bound, and these are the determining sets that work. So once we have these clean approximations, what we prove is that actually in this setting, if you have approximations that are clean, then the groups must actually be infinite for large enough I. And this gives us a contradiction, because we were assuming that for all I, the fundamental cover of each xi was compact, and so the fundamental group had to be actually finite. And we are done. And well, with this, I just like to mention that we did have to rely a lot on these tools, more from geometric group theory, about looking at the structure of these determining sets, and actually playing a bit more with these sort of tools, but which was a new when you compare it with the proof for the smooth case. And well, I think this is a good place to stop. Thank you very much.
Thank you, Jaime. Do you hear me?
Yes, yes.
Yeah. Thank you very much for your talk. Is there any question for the audience in internet? I think there's one question. No, it's not. And from the people here in the in-person audience.
Yeah, hi Jaime. So
hi.
I have a question. It's more on the topic of the pi1, not like the diameter bounds, but are you aware of like any connection between the fundamental group and the homology? So like the Jiggly-Durham homology? Is there like any Hurewicz theorem or something like this, or like any connection at all at this point?
No, I believe it is still open, like to actually figuring out all of these structure built by Jiggly, how it relates to these other constructions, which is more like topological, right? So I believe it is open totally. Like there's a lot of work to do in that setting.
I see. Okay, we have another question.
Hi, Jaime. Thank you for your beautiful talk. I was wondering, well, if I remember correctly, one of the key results of SER was that if a simply connected CW complex has, a simply connected CW complex has higher homotopy groups finitely generated. So my question is, if you can say something like that for higher homotopy groups in your setup. Actually, the question is probably that if you have a sequence of CW complexes that are finitely generated, can you conclude that the higher homotopy groups are finitely generated and give a bound of some sort, as you for the fundamental group?
I don't think so. You will need to, I believe, impose like more things on on the elements of the sequence. I don't think it's enough just to have PW complexes, because I mean the thing with the Gromov-Hausdorff convergence is that, as I said at the beginning, it's not very reliable to expect things just to survive under the sequence. So I think you would need to impose something. I mean, in curvature, yeah, sure, because we have these results, but something weaker, maybe, I don't know. I don't know. It's just that in the end, one relies a lot on actually having some other structure. Like, for example, for the case of the universal cover of the RCD spaces, yeah, you have this construction of the delta covers, which is very general. But to actually prove that the discovering process stabilizes, you do need to rely on some geometric information, like the growth of the volume of things, and having a Bishop-Gromov inequality. So you need a little bit extra. So for your question, I don't know. I don't expect it to be unless you ask for something else.
Okay, I have a last question, I guess. So where did you use that? Now we know that the universal cover is simply connected, or like the last argument, I mean, the proof that you gave, could that work for revised fundamental group?
Yeah, I think it. No, it doesn't work, because at some point, when we are working with proving that these Fi are clean, one needs to construct the determining sets, which are given in a very particular way. And we had the candidates, and we do need to rely to prove that they're actually the determining sets, that we are working with the fundamental cover, like the real one. So maybe you could modify the proof, but at least from what I recall, we really needed that. We were dealing with the fundamental groups, like the proper fundamental groups.
Okay, thanks very much. So thanks again to Jaime, unless someone has a super quick question in the internet. Nope. Okay, so thanks, Jaime.